Good morning and good afternoon, and welcome everyone to this new edition of webinar from u-blox. Today we're going to look into future-proofing EV charging infrastructure with wireless connectivity, and more specifically look into the landscape of wireless technologies, architectures, and standard in EV charging applications. So this webinar is recorded and will be sent to you automatically. You will find the presentation in the handout as a PDF, and we will have a Q&A session at the end. So you can already prepare your question as shown on the screenshots here, and we will take it at the end, but please feel free to ask them along the way. In this webinar, we will look into the EV charging market, use case and drivers for wireless communication, suitable technologies and standards, design consideration, and then how to get started. For this webinar today, we have Stefan Berggren, who is the product marketing manager at u-blox, and Diego Grassi, application marketing manager also at u-blox, and myself, Agnes Derderia, product communication manager, and I'll be your moderator. A little bit more about our speaker today. So starting with Stefan. So Stefan joined u-blox in 2016 as a senior product marketing manager for short-range radio. And he has a long experience in mobile telecommunication industry and specifically in business management and product marketing activities within industrial segments, focusing on Bluetooth, Wi-Fi, and smart building and smart city. Our second speaker is Diego Grassi. He joined u-blox in 2014. He's currently senior principal application manager. He has 25 years of experience in the semiconductor industry and in product management and business development. So now handing over to Diego for the EV charging market overview.
Okay, thank you very much, Agnes. Good morning, good afternoon to everybody. Welcome to this webinar. Let's start. Yeah, okay, here we go. Let's start with this webinar with an introductory market overview. We all see that demand is rising substantially for electric vehicles. So a market that, according to analysts, is expected to reach globally 136 million units by 2030. And operating alongside the EV market, we have the EV supply equipment market, where we also see an explosive growth. This is in fact an industry that will have a compound annual growth rate of 36% over the next decade. Now, the implementation of effective EV charging system is fueled by several factors. So we have government initiatives getting rolled out to drive the EV charging infrastructure. And as a matter of fact, in order to optimize charging time and maximize the driving range, essentially there is an intrinsic need to for all EV users to get charging points deployed massively in many private and public areas. So we see essentially a great number of EV charging points being deployed at home, at work, in many commercial venues such as retail stores, in shopping centers, hotel, restaurants, hospital, parking lots, and there is a clear need to get charging station when EV users are in transit along the public road infrastructure. So the number of charging points is growing, and over the years, charging units have evolved from being traditional non-connected hardware to devices that are now smart devices that rely on wireless connectivity technology. In fact, 58% of trying to see if I the pointer. So 58% of the total EVSE installed base in 2024 is expected to be networked with cellular or Wi-Fi. Let's see now. So let's have a look at what are the use cases and the key driving factors that drive the adoption of wireless communication in EV charging application. And let's start with local connectivity. Both Bluetooth and Wi-Fi technologies are adopted to establish a communication link between users or installers and EV charging stations. Generally, a controller board can manage local connectivity, for example, with a nearby smartphone to essentially provide a graphic user interface. And the EV charging station can also use Wi-Fi connection to home or to commercial building networks. And eventually also the charging station could also be part of a Wi-Fi or a Wi-Fi mesh network that coordinates the communication between several charging points at site. When it comes to backend or end-to-end connectivity, wireless backend or end-to-end communication, wireless connectivity between the highly mobile electric vehicles and the charging subsystem is necessary for several use cases. We see, I don't know why there is a page 12, yep, but okay. We see essentially user can locate charging points, they can monitor charging availability, charging point availability, and easily manage payments through cloud connectivity. Do we see, Agnes, do you see a page number on the?
Yeah, I see a page number, but just to continue, that's fine.
Okay, you say just
when we share.
Okay, so cloud connectivity essentially just to get user to exchange and collect information such as the state of the charge or book the slots for charging requests. And this information can be provided also to so-called EV charging aggregators that can coordinate charging plans and select optimal routes for moving vehicles. With wireless connectivity, both charging point operators and charging point owners can also remotely monitor and maintain charging stations, and through these essentially optimize energy consumption and cost. For example, setting charging to start based on optimal market price schemes, and this is generally at night where rates are lower. Then wireless connectivity will also be an enabler with a forward-looking, let's say, approach to this. There will be an enabling factor for dynamic load management, still with major benefits in terms of energy consumption. Safety can also be increased, for example, when there are several charging points in the same property. Charging events can be remotely stopped based on alarm notification and then can be later rescheduled. And eventually, cloud connectivity enables also the so-called vehicle to grid, so bidirectional charging. This is when essentially there's a possibility to remotely control when energy flows both into the vehicle or out of it. So this means that via special connected charger, an EV battery can both take energy from the grid and give it back to it. Okay, I have some problem in flipping this. Okay, here we go. So another example of front-end communication. Here we see essentially wireless connectivity can be also used in static wireless charging. So later, Stefan will provide more details about this interesting use case, but this is essentially related to when energy is transferred from the grid to the vehicle, from the grid to the vehicle, using an inductive wireless power transfer, while the EV is parked over a wireless charging pad. We see here that EV supply equipment come with different form factors and feature set, and we should consider that different installation types and business model translate to different network topologies, different network connectivity topologies. So the EV supply equipment using, for example, in public charging infrastructure, such as here poles essentially along the road or micromobility hubs. In this case, you use end-to-end single charging nodes connected via cellular to the cloud, or a concentrator node connected locally to a star network and then later to the cloud. So charging units used in commercial venues such as hotel, workplace parkings have multiple charging nodes connected in a Bluetooth or Wi-Fi mesh network, and then are connected to the backend still via IP, or they can rely again on a cellular connection as a primary or a redundant channel to the cloud. Wall boxes, so the so-called wall boxes used in domestic environment or charging installations using in multi-family installation, can be again end-to-end single charging nodes connected to the cloud, or multiple charging points connected to a residential cellular gateway. And eventually here we have an example of portable charging boxes. These are the typical level 1 AC chargers stored in your EV trunk, or even more advanced type of DC chargers that are equipped with battery pack. And in this case, you can use cellular and also GNSS connectivity, so GPS connectivity, to enable tracking and theft protection functions. Again, some other guidelines related to design. So we should consider that different forms of charging station can serve multiple use cases with different connectivity bandwidth requirements. This is particularly relevant when it comes to cellular connectivity. So you see that the large majority of charging units are in fact generally embedded application without a display that require low throughputs to upload or download small packets of parameter data from or to the cloud. And in this scenario, LTM is the best form of cellular connectivity. And we will go later into the details of what does LTM means. There are also emerging cases of or new cases of new use cases, such as the high-end charging pole station that are equipped with feature-rich displays, and these are generally used to monetize, advertise the advertising space on the EV charger. And this type of equipment requires higher connectivity throughput and generally adopts LTE Category 1 or Category 4 modems. Another aspect related to the installation and to the design is related to the place of installation. You see here an example in a parking lot. So if most of the EV units are installed outdoors, there are also underground installation, and this affects cellular signal propagation. So this is the case where a proper antenna designs and the use of LTM or narrowband IoT connectivity can help to optimize the link to the backend infrastructure. Okay, now I hand over to Agnes. We have our first poll.
Yes, thank you, Diego. So let me just move to just one more slide. Doesn't want to. Yes, here. So we are very interested to see what you think about the EV charging market, and we would like to start with the first question. So what we would like to ask you is, what are you developing for EV charging? So you can select one or more. So is it EV charging station, onboard EV charger, or others? So I'll give you a few seconds to answer, and there will be more polls, so be ready to reply. I wanted also to remind you that we have questions, so feel free to ask your questions already now. So I see that some have been voting already. Giving you another second or two, and I will now close the vote, and I will share it with you. So actually we can see that EV charging station is #1, and then there might be other applications, but that's a good indication. So let's continue to the next question. So which use case is of interest for you for EV charging? Again, select all that applies. Is it smartphone, graphical user interface via Bluetooth? Is it internet connection with Wi-Fi and/or cellular? Or is it wireless EV charging ACD? So again, giving you a few seconds to vote. This is very interesting to get your feedback so we can integrate that into our presentation. So feel free to vote. So I think I will now close the vote and then again share it with you. So it seems like it's a bit spread out, but internet connection seems to win it. So, and then the last question for this time. What is your yearly consumption of modules for EV charging? Is it less than 1K? Is it between 1 and 20K, or is it over 20K? So a little bit to know what is your interest here, again, to make sure that we deliver the best for you. All right, so I think I will close the poll now and share it with you. And it seems like it's less than 1K. All right, very interesting. So thank you again for your participation. And now back to the presentation, I think, and back to Stefan, I believe. The clicking didn't work well.
Perfect. So good morning and good afternoon also from me. So I will continue with the standards and technologies. Yeah, so starting with the big picture. So intelligent wall boxes and charging stations have an increasing need for coordination and communication between various mobility and energy entities. And to manage this, the charging station need a connection link with the EV itself, as well as with the cloud for backend services. And the cloud connectivity can be achieved via fixed Ethernet connection or then wirelessly via home or building infrastructure. Or it can then also go directly via LTE to via cellular connection. Consequently, the communication flow could be divided into backend communication, so that is the communication between the charging pole and the backend service, as well as a front-end communication, so that is communication between the charging pole and the EV. From the charging station, there is a communication flow with data related to identification, charging process status, next information, etc. that is used by third-party operators such as the mobility service provider, charging point operator, or grid operator. In the opposite direction, there is a communication flow with the aim to control the charging process. And for smart home and building charging pole installation, the communication flow can also go via local energy management system to optimize multiple resources that are coordinated with the electric vehicle. So that could be heat pumps or solar energy systems. And as Diego said, ultimately, when the EV charging solution is fully integrated with the grid, the EV could store energy when produced in excess of demand and supply it to flatten out peaks in consumption. And there are a number of, the flipping it does not really work so well here. So there are a number of open and proprietary protocol used for the backend communication, including IEC 63110, IEEE 2030.5, EBUS, OpenADR, and OCCPP. And the two main alternatives for the front-end communication is CHAdeMO and ISO 15118. And of course, open standard for web communication flow are essential for ensuring interoperability. And again, Wi-Fi and LTE can be used for the backend communication to provide a robust and secure IP pipe to the cloud. And Wi-Fi is the only standard that is then defined for the wireless communication between the charging station and the EV itself.
Stefan, you can use the arrow on your keyboard to change slide. It seems that the
maybe easier.
Very well.
It does not work. Yeah, okay, it takes time.
I can click
So
for you if you want.
thank you for that. So the charging station typically consists of a power socket board that safely delivers and accurately measures the energy transferred from the vehicle to the charging station, and the controller board that manages security, services, and connectivity to remote server or party. And this webinar addresses the communication block of the control board and its host interface. And of course, we have a focus on the wireless connectivity. So the controller board can manage local connectivity with a nearby smartphone for providing a graphical user interface as discussed before. And here we'll, of course, most often using Bluetooth LE, but it could, of course, also be Wi-Fi. For the wireless inductive EV charging and for connection through pantograph, etc., there can also be a Wi-Fi connection between the charging station and the EV. And then the charging station can also have a Wi-Fi connection as an option to then connect to the home or building Wi-Fi infrastructure if not having cellular connection or being as an alternative. The charging station could also be part for Wi-Fi mesh network that manage communication between several stations at a site. Then, of course, the cloud connectivity can also be managed via mobile network. And again, we will later in this webinar address suitable LTE technology for this. And finally, the charging station could be integrated with a smart home or meter network running Zigbee or Thread, or even Matter of Thread in the future. So next slide then, please. Thanks. So there is, I think Diego explained about this, but there is a move towards more convenient and hassle-free EV charging where we're getting rid of the cable through wireless charging, or when the robot arm or pantograph connects to the charging station to the EV, and that is called ACD, Automatic Connecting Device. And both ACD and wireless EV charging requires a wireless communication channel between the EV and the charging station. And this is defined by ISO 15118. So some words about this standard. So it's an international standard defining a vehicle-to-grid communication interface. And this is then for bidirectional charging, discharging of electrical vehicles. And the standard covers all 7 layers of the OC model, where -1 defines the overall use cases, -2 and the second iteration, -20 defines the network and protocol requirement. And then this new release 2020 includes this wireless power transfer and automatic connected device where you have the need for Wi-Fi. It's also in this version where you have inclusion of the bidirectional power transfer for real smart grid support. And the -8 defines then the physical and data link requirements for the wireless communication. And good material for this could be found in the v2gclarity.com that we used the picture from. So that was it. And then I think it's time for Paul again.
Yes, thank you very much, Stefan. So again, we would like to get your feedback on a few things. So next question is about the technology you're using. So which short-range radio connectivity technology are you planning to implement or are already implementing for your EV charging application? So you can select all that applies. Is it Bluetooth? Is it Wi-Fi 4, Wi-Fi 5, Wi-Fi 6, or maybe not only above, or you haven't decided yet? So giving you another second to answer. And we're sorry about the the mouse being a little bit having his own life today. So I think I will now close the vote and share it with you, so you can also see what are the answers. So it seems like Bluetooth and Wi-Fi 5 are the most interesting for you. So now another question. So actually it's the similar question, but when it comes to cellular technology. So which cellular connectivity technologies are you planning to implement, or are you already implementing for your EV charging application? Again, you please select all that applies. Is it LTE-M, LTE Cat 1, LTE Cat 4, or none of the above and you haven't decided yet? So giving you a little bit extra time to answer. All right, I think I will close this question and share it with you. And it seems that LTE Cat 1, LTE Cat M1 and Cat 1 are the most interesting for you. And then finally, last question, and then and then it will be your turn to ask us questions. Please remember to use the tool for that in the GoToWebinar. So it seems that question a little bit issues to be launched. So what are your main criteria when selecting a connectivity technology? Please select only the top 2 for this. So is it throughout performance, throughput performance, future-proof, total cost of ownership, if it's a large ecosystem and standardized technology, or if it's about security and robustness? Again, please select the top 2 for this question. And promise this is the last one we will ask you. And then I think we need to hurry up for the rest of the webinar. So I will now close the vote. And it seems that the 2 criteria that are, it's a bit difficult to choose, but it seems that security and robustness, and then come equally future-proof and total cost of ownership. So this is now over with the poll, and I will hand over to, I'm a little bit confused if it's Diego or Stefan.
No, it's Stefan, so I will continue.
Sorry, Stefan.
Yeah, so let us then go over to the design consideration, and I will then start with the for the short range technologies, and then Diego will look into cellular and services. So go to the next slide, please. So I will just briefly touch upon the Bluetooth and Wi-Fi standard evolution. So Wi-Fi 4.11n was available since 2009 and is still the dominating technology for IoT application. It operates in the 2.4 GHz band and 5 GHz band and uses multiple antennas to increase data rates. Then the Wi-Fi 5 came in 2013 and is offering higher data throughput and actually up to 2 gigabit per second, thanks to spatial stream, higher order combinations, and larger, wider radio channel. Then Wi-Fi 6 was introduced in 2019 and very much focus on higher network efficiency. And to ensure overall data throughput is improved. And this is particularly true in congested environments. Wi-Fi 6E adds more capacity with new channels also in the 6 GHz band. Wi-Fi 7 is expected to be finalized next year and focus on extremely high throughput as well as improved latency and jitter. Then moving over to Bluetooth. So Bluetooth LE was specified in 2010, focusing low power IoT use cases rather than audio streaming. That was the main application for Bluetooth Classic. Bluetooth 5 was ready in 2016 and further improved data rate and also extending the range. Then we got Mesh in 2017. And looking into the EV charging use case, the data throughput is not that important, and Wi-Fi 4 is often good enough. However, we expect that Wi-Fi 6 is expected to quickly penetrate the market. So we see that many are looking into future-proofing there, and that was also reflected in the poll. For Bluetooth, I mean, we highly recommend to go for Bluetooth 5. I mean, that is to have the higher data throughput and more importantly, to really stay current with the standards as later versions can be deprecated or withdrawn. I will come back to this later in the webinar. So next slide then. Then we have a number of architectures you need to consider, and u-blox denote these as host-based respective standalone architectures. So the host-based architecture is used when you need higher Wi-Fi throughput and you need full control of the software and have flexibility in your software development. It's also when you have heavy applications that run mostly on the powerful processor running Linux and Android. In this case, the IP stack and the Wi-Fi drivers are running on the host module, whereas the short-range module are running the lower layer protocols with the physical MAC. And the interface is SDI, USB, and SPCI Express. Alternatively, if you have a more simple MCU and higher bandwidth is not a requirement, the standalone module controlled with a simple Alt-80 command is the best fit. And standalone modules come fully equipped with the Wi-Fi and the Bluetooth stack and offers basic communication service. And that is thanks to our 80 command software called uConnect Express. And here the communication goes, for instance, through a UART interface. Another option to consider is whether to use automotive or professional grade modules, and both of these are going through extensive qualification according to ISO 16750. And automotive grade modules also qualified strictly according to ASC Q100, and such modules feature excellent immunity to severe mechanical and electrical stress. And by that also they have characterized by lowest possible field returns and have very long product availability and life cycles, and also follows the automotive quality processes. So EV implementation are of course always automotive grade, whereas in the charging stage we primarily see professional grade modules, but some also implement automotive grade there. So going to the next slide. So in this table, I try to summarize what type of Wi-Fi module to use for the charging station and the EV implementation. And note here that I have separated the EV charging station for the back-end communication and the front-end communication. So starting with architecture, many charging stations with more advanced graphical user interface and large display are using host-based host processor running Linux and Android, and therefore have the need for a host-based Wi-Fi module. More simple charging stations that still have the need for wireless connection via Wi-Fi are served through an MCU and a standalone Wi-Fi module controlled via 80 command. For the EV itself, we see primarily host-based architecture, whether the host is implemented as part of the Linux-based TCU or is in a separate electronic control unit, ECU, that is running AUTOSAR. And here the ISO 15118 stack is running on the host implementation. Second choice is then about whether to use Wi-Fi single band or dual band. And for front-end communication, we see always dual band that's required by 15118-8. For the back-end communication, it's again a mixed bag, I would say, where some focus on cost and rely on a simple Wi-Fi 4 BGNN Wi-Fi module only supporting the 2 to 4 gigahertz band. Then, of course, going further, we will also see even triple band solutions where using also with the support also for the 6 gigahertz band. The third choice is whether to go for multi-mode modules supporting both Bluetooth and Wi-Fi to be able to manage all the use cases we have been talking about. Again, I mean, the front-end communication, that is only Wi-Fi, so no need for multi-mode in that. However, I mean, those players that will implement both the local interface for configuration as well as the backend connectivity should, of course, benefit from a multi-mode module. If your charging station also have an LTE connection, it makes also sense to have a Wi-Fi module that has an LTE filter to avoid interference with LTE bands close to the Wi-Fi frequencies. If you implement a charging station that manage both front-end communication, back-end Wi-Fi communication, then you need a module that can run simultaneous Wi-Fi access point and station. Because then at that use case, the charging station is connected to an access point, a Wi-Fi router in the house, and at the same time it acts as an access point to the electrical vehicle. And then, of course, there are many other things that you need to consider. So, for instance, the Wi-Fi release that we asked about, and here I would say, I mean, that really depends. I mean, many focus on cost, and again, see that Wi-Fi 4 is meeting their communication need, and ISO 15118 also mandates 11N. But if application require high data throughput, then you should go for Wi-Fi 5 or 6. And again, I mean, Wi-Fi 6, I mean, that is primarily then for spectrum efficiency, and that is important when many devices are fighting for the available bandwidth. So on the qualification, I mean, we see again primarily professional modules that are selected for the charging station itself and automotive grade for the EV implementation. And there are several other options to consider around security, antenna configuration, and coexistence, etc., that I don't have time to elaborate in this webinar. For Bluetooth, there are less options to consider. Let's see if we can move. Now, so customers seeking a solution for local monitoring and configuration, the recommendation is to go for a standalone module, whereas customers that need to manage both local configuration as well as backend connectivity, I mean, then should of course go for a standalone or host-based multi-mode module. Wi-Fi 5 is highly recommended to stay current with Bluetooth 6 releases, and especially the 2 megabit physical bearer is important for the EV charging, for instance, for firmware upgrades. The longer range that is received with a new physical bearer coded PHY, I mean, we actually measure up to 1.5 kilometer in distance of line of sight. But I think it's rather the capability to offer coverage through walls in indoor environments that drive the need for the feature. But I see limited value for EV charging for this. And again, also professional grade mode are primarily selected for the charging station, especially if only Bluetooth Low Energy is used. So u-blox has, of course, a broad range portfolio of pre-certified short-range module that could fit with the different need. I mean, pending the charging point product type, the communication need, and the product grade. For the more simple charging stations that only requires Bluetooth support, we recommend our ANA-B and NINA-B modules. ANA-B is a small seat-based module that is only measured 6.9 times 6.5. Both modules are supported Bluetooth 5, and there are different feature set, performance, and antenna solution that can be tailored for your needs. For lower-end charging stations, NIDA comes also with Wi-Fi versions, NINA W1, that is a Wi-Fi 4 single-band module with our Uconnect Express software. And for more advanced charging stations, there are 2 Wi-Fi 4-based host-based alternative with the Lily W1, that is a Wi-Fi single-band, or Maya W1, that is a dual band Wi-Fi 4 and Bluetooth 5 solutions. Both these models are very compact and come with multiple antenna versions, and including built-in PCB antenna. And LTE filter is also an option for these. And for the more advanced application requiring Wi-Fi 5 or 6, but also automotive grade, then you need to look into our Jody W family. So with this, I hand over to Diego for continuation.
Okay, thank you very much, Stefan. So moving to end-to-end connectivity, let's have a look now at the forms of cellular technology and connectivity plans suitable for EV charging application. You can see here, essentially, the cellular technology is growing in complexity, introducing different types of specification while moving towards 5G. And if you focus on the lower part of this graph here, so you see that the new LTE categories that are candidate for EV charging station are LTE Category 1, Category M1, and narrowband IoT. So these are the best option we see for future-proof EVSE designs. LTE-M and Cat1 in particular are the best option for mainstream, so-called mainstream type of charging stations. And LTE-M is notably brings benefits in terms of higher connection density. So this is related to the number of IoT applications that can be connected simultaneously to one node of the cellular network. With LTE-M, actually, we can scale up to 50K nodes, 50K points to connect it to the node. And this characteristic is particularly important when we think about the very large number of IoT devices is being deployed particularly in urban scenarios where also EV charging stations are actually deployed. Another aspect of LTE-M is extended coverage. This is a feature that essentially translates in better propagation of the radio signal and that allows to reach charging units in hard-to-reach places. We saw the example of underground parking lots. And then low device complexity, so single antenna, and this translating the, let's say, simpler and lower cost type of designs. So the LTE Cat1 and Cat4 are optimal solution for high-end or higher-end EV charger. We saw the example where we have a high resolution display, so you have a need to upload or download the data from the cloud, or in concentrator and gateways where you might need a better latency response, for instance, to fulfill the demand on EV charging aggregators. Here we present a selection of u-blox cellular modules. Our SARA R4 and R5 LTE globally certified LTE modems are suitable for residential, commercial, and public EV charging station. These modules are available also in variants with integrated GNSS chipset. And as we said, these are, we saw before, these are optimal solutions to enable tracking functions, particularly useful for portable EV charging units. So let's think about the large number of fleets that are now being implemented at corporate level. So EV charging vehicles are used at corporate level or rental car companies. So there's a need also to locate these tools that are generally stored in a trunk, but having a tracking function will help in implementing better fleet management solutions. Our LTE Cat1 and Cat4, Lena R8, R6, and L6 are optimal solution for higher-end EVSE platform. You can see essentially that our solution, our cellular modems provide a pin-to-pin mechanical compatibility between different cellular technology options and form factors. So this helps to design, to enable design flexibility and an efficient scalability for EVSE platforms that can generally be designed to address multiple regions or multiple market segments. Let's move to just an overview of u-blox IoT services. So in order to complement our cellular, short-range, and positioning hardware components, u-blox has developed Thingstream. Thingstream is a cloud-based delivery platform and administration interface for enterprise services. The Thingstream platform delivers IoT connectivity, security, and location services, and it brings an enterprise-grade MQTT broker along with visual programming capability. It allows to simplify the enterprise integration, and this is done with a flexible pricing plan, with flexible pricing plans tailored to specific IoT use cases and applications. So our communication as a service combines true global connectivity with fixed price, with a fixed enterprise global MQTT network that works seamlessly in 190 countries. So we essentially bring ubiquitous seamless roaming for EVSE platform that are or can be deployed on a global scale. So with u-blox connectivity, we simplify the complexity in the integration of your EV charging station with cloud infrastructure, and we can accelerate your deployment, reducing both the time to market and the total cost of ownership of your platforms. Another aspect of design is related to security. So security, actually preserving safety, security, and as a matter of fact, the resilience of the grid infrastructure. All these are certainly primary objective for any future-proof EV charging platform. And to fulfill these requirements, u-blox provides also a rich set of IoT services, security services, to help protect your business, your data. And this is done through a world-class, scalable, symmetric key management system. So we don't have now today time to go in the details, so we should defer the detailed description of our security solution for future discussions. But I like to mention at least our certificate lifecycle control. So this is a service that delivers an out-of-the-box onboarding to IoT cloud platform with total control of device certificate lifecycle. And let's move now to a final part of our webinar with some examples. So I like to give some examples related to u-blox solution for typical EVSE architectures.
We need to go a little bit faster, Diego.
Yeah, just have a problem in flipping. Maybe you can help to flip in the next slide. Okay, here we go. So here we present a simple block diagram representative of entry-level EV charging units. These are typically RTOS system with a power socket board here, an embedded controller for service processing metrology, and we show some example from the rich portfolio of NXP MCUs. And if you look at the pink colored areas, you see the typical hardware components and service building blocks that are used to enable local and end-to-end connectivity. So there is actually a wireless communication unit equipped with our SARA R4 LTE module to enable a primary or a backend channel to the cloud. There is an INA-B4 wireless CPU that is capable to support BLE for users when they adopt a smartphone as extended user interface, or for installers during onboarding, configuration, and monitoring of the EV charging point. The same NINA-BU can be used, can support concurrent use of Thread and Zigbee protocols, generally used for local connectivity with a local mesh network or with the utilities metering infrastructure. In the upper part here, you see essentially the cloud connectivity infrastructure architecture enabled by u-blox Thingstream service delivery platform. That, as we say, it's essentially bringing a global form of IoT optimized cellular connectivity for communication with backend. And when we think communication backend, it means essentially different stakeholders from end user to grid operators, charge point operators, up to different type of industry third-party stakeholder. And a second example is related to a Linux-based architecture, generally using a mid-tier platform. Here, if you focus the attention on, again, on the wireless communication unit, you can note our Lena R8 Cat1 module, a single antenna LTE modem. And for the local connectivity, our Maya W1, a multi-mode BLE and Wi-Fi module. The Maya W1 is a small and flexible host-based multi-radio solution supporting Wi-Fi 4 and Bluetooth 5 communication. And with this module, you can provide multiple operation modes such as access point, station, Wi-Fi direct, and also combination of these various modes. A third and a final example, still an higher an higher end type of Linux-based architecture, where in this case the wireless connectivity unit is equipped with a LTE Cat1 or Cat4 modem, or LARA R6 or LARA L6 category module. And while the local connectivity is enabled by JODW2, which is a short range, is a multi-mode BLE and Wi-Fi host-based module supporting dual band Wi-Fi at 2.4 GHz and 5 GHz, and as well as a dual mode Bluetooth 5, supporting also BLE low energy and extended range. Again, also this module is optimized in particular, as Stefan said, for parallel operations, having a larger throughput. We have Wi-Fi 5 connectivity and Bluetooth, and it can provide simultaneous access point. It can be used as station or Wi-Fi direct operations. So we conclude just with a brief overview of u-blox development tools that can be considered to get started with your new designs. You see here, essentially, we have a rich set of evaluation kits, application boards, and blueprint examples that can be used as reference designs. And a final condensed overview of the specific development tools designed for the comprehensive portfolio of NXP MCUs. In order to facilitate the implementation of the architecture, some of the architecture I just proposed, u-blox has essentially provide a series of M.2 cards on our host-based portfolio, including Maya W1, JODW2, and JODW3. And these boards can be used for evaluation in combination with NXP host processor and their corresponding evaluation kits. We also have micro SD adapter boards that combined with M.2 cards can also be used with, for example, IM8 Nano or IMX8M Mini EVK. And consider that the software is also fully integrated in MX MCU Espresso for NXP IMX RT family MCUs. So we conclude here this webinar. I think thank you very much for your attention. We look forward for possible future discussion related to your design, and I hand over to Agnes for a final Q&A session.
Thank you very much, Jaco, and thank you very much, Stefan. Just a quick reminder here, for further information, we give you here some contacts and a reference to white papers from u-blox, but also from NXP. So now over with the questions. So we've received a few. I think we need to put on the webcam, so that will be easier for us all to deal with those questions. So I think the first question is actually for you, Stefan.
All right.
Yes. So question was, you mentioned the Uconnect for standalone modules. What is that?
All right. So Uconnect Express, I mean, that is really a tool or software that we're providing to, a tool that will make it that you do not need to focus on complex real-time embedded software development yourself, and also avoid major redesigns of your legacy system. So this is really an extensive API with 80 commands, and it's something we developed for more than 15 years of time. So it covers functionality for Wi-Fi, Bluetooth, mesh, and security, and also cloud connectivity, important for these type of use cases, as well as system interfaces. So it's really, I mean, out of the box software that you can integrate your application through.
Great, thank you. Next question is for you, Diego. You show different cellular modules from form factors. Do I need to design different PCBs in case I want to use SARA R5 in a connectivity board for an entry-level charger, and R6 in a high-end variant at the same EV charging platform?
Yeah, thank you. Very good question. So indeed, we show that our SARA, LARA, and LIN modules do come in a slightly different form factor. SARA is the smallest with 16 by 26 millimeter. Our LARA is 24 by 26 millimeter, and our LIN has a slightly squarish and larger form factor, 27 by 30. But indeed, all these modules share exactly the same pinout. So this means that the different modules can be alternatively mounted on the same PCB design. So this translates into a good flexibility to our partners that can design one only PCB and then think about having a scalable EV charging platform that can be used in different variants or variant of their application on high end, requiring lower throughput and a lower end requiring lower throughput, and a high end or higher type of complexity EV charging station for higher throughput. And this is done reusing the same PCB.
Okay, thank you, Diego. I have another question for you, Diego, and Stefan, maybe you can check the one that is in the question panel in the meantime. So, Diego, back to you. You mentioned LTE-M, Cat1 and Cat4. Can you clarify what are the differences in terms of throughput?
Yeah, so first we should clarify that LTE-M is a new specification, a new form of LTE specification that requires to be enabled by a new RAN. So essentially it requires a network infrastructure. LTE-M is now a consolidated technology, has been introduced since more than 3 years, and it's largely available in the United States, in Japan, Australia, and several parts of Europe and Asia. And the typical throughput of LTE-M is in the range of 300 kilobytes seconds in downlink and 370 in uplink. LTE Cat1 comes in now in 2 flavors. So the typical throughput is up to 10 megabit in downlink and 5 megabit seconds in uplink. And LTE Cat1 comes now in a newer variant, so an so-called LTE Cat1 bis without antenna diversity. So this can be an option to simplify the design and essentially reduce the cost of the overall design or simplify the design. We should also point out there are also some drawbacks. Essentially, LTE Cat1 with a single antenna translate also into a slightly lower sensitivity, so 3 dB sensitivity loss, and also a slightly lower throughput in downlink on typical on-cell edges.
Okay, thank you, Diego. Stefan, do you want to take this question we have on the question panel?
Yeah,
or
yeah, so the additional question here, hope that we will see the PowerPoints. Yes, I think that we will share after this.
I will share, yeah.
And then why these EV kits are in M2 slot form factor. And I would like to say that, I mean, we are doing these M2 card primarily for evaluation purposes, and as Diego explained, I mean, fitting very well, for instance, together with the NXP evaluation kit. But I mean, this is for evaluation purposes, but we also provide these as a commercial product that we have seen an increased interest. And then, of course, I mean, we are also providing normal EV cases that Diego also explained about in his presentation parts.
Okay, thank you very much, Stefan, and thank you very much, Diego. I think we will end the webinar now because it's 10. So thank you everybody to the presenters and also for the listeners. And this webinar has been recorded, so you will get the link automatically. And for the presentation, I saw there was one request, but otherwise, if you didn't have time to download the PDF, contact us and we'll come back to you with it. Thank you very much. Have a good day and good evening, and talk to you soon.
Thank you.
Bye.